Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another Engineering Mechanics video. This time we're going to look at the simplification of a distributed load. So let's have a look at the problem. Okay, so here's the problem. We have a distributed load here across a beam. So we've got two linearly varying loads. So let's have a look at how we solve the problem. Let's go to the next page. All right, I've just repeated the problem there. So we're wanting to find out where the equivalent single force is, or what the equivalent single force is, and where it's located on this beam measured from A. Now, maybe you can tell where it's going to be just by looking at it and seeing that it's symmetric, but we'll go through the process that you would do if it wasn't symmetric and see what we get for our answer. So our solution will break our load up into just simple shapes. So we can see we've got, or we can break it up into one rectangle across the whole beam that represents a uniform loading, and then sitting on top of that will be two triangles. So let me just quickly draw what I'm talking about there. So I'm just working on my iPad here, which is why I'm looking down. All right, so you can see a rectangle there, and then you can see triangle on top, and then another triangle on top over here. So we've got three simple shapes, and we can just use the geometric properties of areas from tables in our textbook or other ones that you might be able to find online and work through the problem. So drawing our beam with our uniformly distributed load with a magnitude of 3, oops, should stop using that. Let me go up here. Magnitude of 3 kilonewtons per meter over the length. And then sitting on top of that, we've got a triangle on the right-hand side. Again, so its total force here, or distributed load here, is 6 kilonewtons per meter. So for just the triangular bit, we've got 3 kilonewtons per meter, and we've got the same on the other side. Okay, so firstly, looking at the rectangle, so we know that the force acts through the centroid of the area, or the centroid of the shape. So for a rectangle, the centroid is just at its geometric center, so that one we can put in easily enough. And its magnitude is the magnitude of the distributed load in force per unit length. So you've got 3 kilonewtons per meter, and the total length is 6 meters. So we can come up there and we'll get, 18 kilonewtons. Then for our triangular areas, the force will act through, again, the centroid of the shape. And for a triangle, the centroid of the shape is 1/3 along the length of the triangle. So we're wanting to know the position in the horizontal direction. So that will be 1/3 of this length. So this length is 3 meters. So the centroid will be 1 meter from this right-hand side here. So we can put that in, and the magnitude of that is the area under the loading curve. Okay, so we just want the triangle. So it's a half times 3 for the height here and 3 for the base. So that gives us that area, and then of course we've got the same over on the left-hand side. So now we can just add all that up to get the resultant force. So resultant force is some of the forces in the y direction, taking downwards as positive in this case. So we have 3 times 6 for the uniformly distributed load, plus 2 lots of half times 2 times 3 for the linearly varying distributed load. And that gives us a total of 27 kilonewtons, if I've done my maths right, acting downwards. And then from that, we'll have a single resultant force that we can put on the beam. Now, normally let's see what I've done here. Yeah, so normally we don't know where this is going to be. So we would arbitrarily put it anywhere along the beam and just denote the position with our unknown variable d here. In this case, because it's symmetric, I know that it's going to be at the center. So that's why I put it here. But if you didn't know, that's okay. Just put it somewhere and then put d and then do the maths to find out. So let's see that the maths confirms that this resultant force here will be at the center of the beam. So equate moments to find d. So we have the resultant force times the distance from its line of action to A, and then the sum of the moments over here is the sum of the moments of these three forces that we found in the previous step. Taking clockwise as positive, so we have 27 times d equals 3 times 6 times its perpendicular distance from here to here is 3 meters. So that's where that 3 comes from. And then we have a half times 3 times 3 times 5. So this one here, its perpendicular distance from A will be 3 plus 3 minus 1 is 5. That's what we have there. And then we have this triangle over here. So this force was 1 meter from A. So half times 3 times 3 times 1. And do the maths and we get 3, which confirms that the resultant force is at the center of the beam. Okay, so that's the end of the problem. Hopefully that was helpful and maybe interesting. I don't know. Anyway, see you in the next video. Bye for now.